Do we do stop it? We do stop it. So where is it? Yes, hi. Yes. Yes. So we have finished the electron beams on the slide 8, and today we will continue with the slide 9. And let me show you the slide. Yeah. So electric and plasma are those other types of heat sources that can be used in order to melt metals within the additive manufacturing technologies. Electric arcs is the high energy density heat sources. Can be melt metal, but at lower rate than in the case of using laser or electron beams as a heat source. And heat source relates to the electron beam. So the electron transfer across the arc, but at lower energy density, respect to the electron beam, of course. And at the moment, we're comparing between the arc heat source and the electron beam. The arc characteristic depend actually on the direction of the current flow, and others, for example, sheen gases, field emitters, and so on. And the advantages of the arc heat source over the other type of heat sources is the lower equipment cost. So because in order to maintain the condition that can be used for the electron beam, generally speaking, it's quite expensive in terms of the maintaining high vacuum inside the building chamber. Yes, and it's not easy, to set up the condition for emitting the electron, yeah, to create the electron beam and focus the electron beam in order to locally melt the metallic materials for each layer, for sintering or melting each layer of material during the additive manufacturing process. Disadvantage of the heat source is the type of heat source cannot be focused tightly, and as a result, we have the problem relating to the accuracy. Yes, and for sure, we have low surface qualities of the materials because you please remember about the staircase effects. Yes, and this is actually affected by the heat source because it cannot focus tightly. Yes, the deposition rate is high, but the accuracy is low. So this is something that we could find a trade-off. The gas meter arc welding, the meter ionic gas welding, using the filler wire as the consumable electrodes. So this means like when you perform the welding process, you use the stick, yes, and during the joining process, by melt the stick, and we consume this type of electrode and deposit the molten matter into the area that we, yes, need to join the two different parts, metallic parts. Yeah. The metal is transferred across the arcs to form the molten point. So I just want to highlight that for in the case of metal ionic gas or gas metal arc welding, as you can see from the figure on the right side of the slide, that is the consumable electrode. So it means that during the welding process, the electrode is consumed, is locally melt and deposit the material to the workpiece, or to the substrate, whatever you call. Yeah. Sorry for you. And we have another type of plasma arcs called electric and plasma arcs called plasma arc welding. You know about the plasma is the four type of matters, where we have the ionized gas. Ionized gas is actually the plasma which possess quite high temperatures, can reach around 4,000 degrees C. Yeah. And at these high temperatures, it turns the welding arc into the focus. Yes. We have firstly the ionic gas. Yes. turn the wedding eye into the focused high energy density of as plasma jets. Yeah. And at high temperatures, we can melt the metals to form the molten pool. Yeah. Filler materials can be introduced directly to the molten pool under the influence of the heat source, and we melt the filler materials. Yeah. And in that case, the material is not integrated to the part of the heat source. So the thing is that sometimes you have the heat source equipment which you can immediately irradiate the electron beams and laser, but at the same time you can insert the materials to the part, like in the case of direct energy depositions. But you can also have another type where the filler material do not integrate with the heat source component, let's say. So on one side, you introduce the heat to the surface that need to be melted. And on the other side, you insert the material in front of the wire or the stick. Yes. So in that case, this is the second situation where the filler material is not integral part of the heat source, or is not integrated with the heat source component. It's not integrated with the heat source component. Another type of heat sources, we have the hybrid heat sources, is the combination between the different type of sources. For example, the arcs and the laser can be combined to create the hybrid process. The arc assisted laser welding, yes. In terms of the penetration and travel speed of the laser, which can help to increase the deposition rate for materials. Yeah. And since we can increase the deposition rate, we can somehow reduce the cost of the metal AM system. Yeah. This is expectation, but we do not know in detail about the quality of the material when we increase the deposition rate. Yes, that's something that we need to pay attention to, because when we increase the rate, and normally the accuracy and the quality of the material may be affected. And in that case, we have to consider carefully whether we increase the deposition rate, but the quality of the material is still guaranteed and is okay. But if not, and we have to further develop the technologies. Multi-laser beam can increase the speed of the powder fusion. Yeah, of course. Because we need to keep the laser beam at a certain position for a certain period of time, so that the heat will be transferred enough to the how can I say, metallic powders that can heat up and locally melt and melt the powders materials. But if the traveling speed is too fast, and then the heat transfer to the layer of powders, which is not enough, and then we cannot totally melt the powders. In that case, we may have some kind of defects. And if you use multiple laser beam, and we can somehow increase the speed of the powder, and at the same time we can avoid the defect caused by lack of fusion. So we can increase the speed of the powder fusion, but we cannot increase the speed of powder recoating cycle. Yeah, because it's the matter of using a recoater blade. We insert more material. We use the powder recoater in order to coating a layer. Yes, and this process cannot be how can I say, cannot be faster. Yes. But using the multiple laser beam, which help you to increase the speed of powder fusion by providing more energies. Yes, by providing more energies to the powders. Hot wire application. Yes, you resistive heating to preheat metal filler to improve the rate of melting in molten pool. Yeah. So simply thinking of the fact that we provide additional sources, we provide more energies than enough to assist the process of melting, and therefore we can improve the rate of melting. And that's all. That's the point. That's the point. Or we can use the infra lamp heating, mm, to preheat the building plate, the powder bed, and we can improve the building speed. Uh, yeah, in some case, preheating is necessary because you know that without preheating the building plate or the powder bed, and then we, how can I say, is these components had low temperatures or lower temperatures with respect to the surface that irradiated by the laser, because when the laser shine on the surface, the laser provide heat to the surface of the part that are being additively manufactured. Additively manufactured. The problem is that if the building plate is cool or have a pretty lower temperature with respect to the surface that is currently sintered, and we have thermal gradient, and this causes the the residual stress. Yeah, that's the point. That's the point. And therefore, yes, in many cases, we need to preheat the building plate in order to avoid the large thermal gradient in the uh, additively manufacturing parts, yeah, to reduce the stress concentrations. And infrared heating can be used. Now we turn to the heat source characteristics. So several, let's say, features associated with the heat sources. So we can name some features of characteristics. So, for example, the temperature profiles, the deposition geometry, the feature of the solidification process, and the heat source characteristic as well. For the laser, electron beam, or plasma arc, so we pay attention to the radius and the power density distribution, and we symbolize as the PD. And the two parameters are among those most important parameters. And PD can be calculated by the equation highlighted on this line, where the F, sorry, because I have 4 hour teaching in the morning, so now I have problem, a little bit of sore throat. Yeah. F stands for the distribution factor. P is the total power, B is the radius of the heat source, and RB is radius of the heat source, and I is radius distance. And you can see the relation between the power density, the horizontal deposition, when we change the distribution factor on the right side of this line. And by increasing the F from 1, 2, and 3, the energy is more focused, and we have the power density is concentrated at the center or the axis of the energy beam. Energy beam can be the laser beam, can be the electron beam, or we call energy beam. So if it's more focused, and we have the higher peak temperatures under the heat source for sure, because it's focused. More energy is focused, and therefore the temperatures is rise up. And for the particle fusion, using the laser as heat source, the beam diameter can range from 50 up to 100 microns for wide resolution. And in the first chapter, where we introduce the advantages and disadvantages of several type of additive manufacturing. So, for example, comparison between the direct energy deposition and the Parabec fusion. So we list the features of the energy beam used by the direct energy depositions. So it has the larger diameter of the beam, yes, comparing to the case of Parabec fusion. I mean that the heat source, the laser beam in direct energy deposition has larger diameter with respect than in the case of beam, that is laser beam used for Parabec fusion. So larger beam diameter, meaning that we can improve the deposition rate, but at the same time, the accuracy, yes, and the detail feature will be reduced. Yeah, will be reduced. High power electron beam, yes, with a minimal beam diameter of 200 microns, yes, can be obtained by using magnetic lens, yes, instead of optical lens. So the magnetic lens will used in order to focus the beam, in order to focus and minimize the diameter of the beam, which is around 200 microns. And the energy density of the arc source depends on actually four different factors. So for example, the arc length, the field wire diameter, the arc current, and the nature of the shielding gas. So we need the shielding gas to avoid different kinds of oxidation reactions. Yes, to provide the shield to protect the wedding from oxidation. And now we would like to see more a little bit on the interactions of the heat source and materials. Yes, so I would like to say that is quite difficult to investigate the interaction between uh, the two matters, let's say heat source and materials. So let me divide it into two different cases where we used direct energy depositions and the Parabec fusions. So within the first case, part of the heat can be used to heat up the flying powders. Those powder emerge from the nozzle and traveling through the beam. And the other part of the energies will be dedicated to creating to create small molten pool. Just because it's focused, so we can only transfer these remaining energies to create a small molten pool. Lớp các bạn có người tên là Bảo Dương à? Không có đúng không? Chỉ có Nguyễn Thái Dương thôi. Vì tôi thấy có người tên là Bảo Dương vừa mới access vào trong lớp của chúng ta, cũng khá là lạ. Các bạn lưu ý là cái link của lớp học của các bạn chỉ dùng cho các bạn thôi nhé. Okay, it's not important. These source can be represented as the following density distribution. Yeah. So we have the complex equation to represent the power density distribution. That so far is not important. Yes, and yeah. Let me skip this part because we did not investigate the influence of certain parameters on the power density distribution. But generally speaking, you could see that if we increase the distribution factor F, and then we can enhance, yes, the PD, the powder density at the heat source axis. Yes, we can transfer higher energies to the materials. Yeah, and because it's directly proportional with the F, PD and F. Yeah, in general. In powder fusion, the total heat incident on the powder or the total heat irradiated on the powder bed, uh, and with the total heat, some of them will be absorbed. Other can be reflected until the beam emerge outside the powder bed. Yes. So just want to remind you that, yeah, the energies can be interference during the time it's traveling through the, 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 the area in the building chamber before reaching the materials. So during this time, yes, part of the energies can be lost. Part of the energy can be lost. When it reaches the surface of the materials, some can be reflected, some can be absorbed, but then immediately irradiate or released in the form of heat. And the remaining, yes, can be absorbed and stay there and heat up the material up to the molten stage. Yeah. That's the thing that can be happen in Parabec fusion process. And if we provide high enough power density, yes, and in that case, the energies, if is enough, and the molten droplet can be ejected from the pool just because it provides quite high energies, and the energies provided by the laser is large enough in order to eject the droplet of the molten material from the pool and from the spatter, vung té lên. Yeah. Vì là các bạn đưa một cái lượng nhiệt nó quá lớn, đúng không ạ? Thì sau khi mà cái giọt vật liệu nóng chảy nó nhận được cái lượng nhiệt đó thì nó nhận được quá nhiều năng lượng tự do, quá nhiều cái năng lượng cho quá trình nung nóng, thì sau khi nó chảy ra rồi thì nó lại bị kéo ra khỏi, bị eject khỏi cái khung kim loại lỏng, và nó tạo thành cái sự vung té kim loại. And the molten pool at this moment possesses recoil pressure, or we call the local vaporization, cái sự bốc hơi cục bộ, sự bốc hơi cục bộ. And if the pressure is caused by the local vaporization is large enough, and being larger than the surface tension force at the molten pool, and the spattering is occurred. Spattering is occurred. And we have another equation called the Langmuir equation, is for expressing the alloy element vaporization. And you have the equation. I do not want to focus on this. But please remember that if the heat provided to the powder material is large enough, that can create the vaporization, and some of the alloying elements having low melting temperatures will be vaporized, and you lost alloying element. You lost alloying elements. This means that the chemical compositions of the material in such case is changed, is modified, because of the fact that we lost alloying elements, and then properties will be different from the remaining area of the material where we do not have the vaporizations, and this is unexpected. Yeah, that's unexpected. And I took this figure from a nature paper. A nature paper. This can somehow show shows us the interaction between the heat source and the material. And the heat source here is the laser beam. Yeah, the laser beam will interact with materials. Yeah, and then you have uh, some kind of behavior, the material under the influence of the heat source, and depending on the power of the laser, the scanning speed, uh, the power density distribution, the yes, the factor F, yes, scanning strategy, and we can have some kind of defect like a fusion, and we may have the crack, yes, and we may have also the spattering, yes, spattering of the particles, and we lost alloying element due to the vaporizations of the alloying elements with low melting temperatures and so on. But if you have enough time, if you prefer, if you are interested in this physical phenomenon, and then you can find more on the in the paper. And that's the content of the chapter 3, where we focus on the basic function of the source for the matter AM. And we need high energy to melt the materials. No matter what, the feedstock material in the form of powder or in the form of wire, and we need to melt. We need to melt the materials with the high energy source. Okay, so now let me turn into the chapter 4, where we will focus on the content of computers, solid motors, and robots. So now we'd like to deal more with the design process than the additive manufacturing itself, because we need to design something to be manufactured by the additive manufacturing process. So it's related to the additive manufacturing, and the design is you could see that is a little bit different from the traditional design process for traditional manufacturing process. Yeah, computer aided design. Yes, for the moment we use computer aided design in order to design mechanical parts widely to be manufactured by CNC, for example. So, but at the same time, computer aided design can also be used to
Hình như
design.
là thầy cho chia sẻ màn hình đó thầy.
I'm sorry. Yeah, here. Yes. Yeah, just few words about the new chapter, the fourth chapter. So computer-aided design can be used to design the part virtually by using several kind of software. Mhm. So for the moment, yeah, computer-aided design software evolved significantly from the 2D to a full 3D model. And for those who have some knowledge, or you are familiar with using Inventor, SolidWorks, or CATIA, you will probably know that this software has the ability to virtually assemble different parts to form components. Simultaneously, several kinds of software can perform the simulation to check the function of the 3D models after the assembly process. So in doing this, we can allow the rapid definition of geometry and even the virtual function or the function that can be checked virtually with software in order to somehow firstly somehow confirm that the model can work before you can prototype to check it practically. To check it practically, yeah, just to save cost and time during the product development process, nothing more. And when we talk about the computer-aided design, we can divide it into we can divide this into several kinds of categories. Let's say the high-end software package. So this means that it cannot only be used for to model, to create the model, but can also use to perform some kind of simulation. Yeah. So high-end software package like Katia or Pro Engineer, those can be used for product development. This can be used for model design, let's say, product and process definition, inspection, in-service performance. So this means some kind of yes, control, uh, and even some kind of simulation. Yeah. But, when you perform the simulation in such kind of software, and then the ability is not cannot be compared actually with uh, the uh, the CAE software package, like in the case of ANSYS or Abacus and so on. Mid-range package like SolidWorks and Autodesk Inventor, let's say. So these software have a high degree of functionality at reasonable cost. This means that it's cheaper. Yeah. Have the ability to input and output solid model. Those can be used in additive manufacturing. So for example, the step file, or the on the right side you see the SDL file. So this is actually the surface model files. This is no longer solid, but just the surface model. Yes, and inside is the free volume, because the SDL just defines the surface, and the area restricted by the surface will be printed out in the form of solid uh, during the manufacturing process. Yeah. And low price 2D and 3D software, we may call the open source license, like Mass Mixer. So for example, you can set up for the, let's say 3D printing, but generally speaking, Mass Mixer can be used to set up the model for printing out the polymeric materials, not for metallic materials. In the case of prepared model for printing out with the metallic materials, and you need, so for example, Autodesk NetFab, like uh, the so-called materialize, let's say, it's quite powerful software in order to set up the model for printing out the metallic parts. And let's come back to the low price 2D 3D software, and you can create models easily. You can convert the 3D model files or 3D solid files to the SDL files for the 3D printings. So here I would like to highlight that 3D printing do not employ or do not use 3D printing processes do not use, let's say, the 3D solid model. Instead, the processes need the SDL model or the surface model as shown on the right side of this slide. So each software has its own file format. So some can be very powerful, the other may not as powerful as the other, but in general, they present the possibility to convert into other type of formats that compatible with ADF as additive manufacturing, like in the case of STL5, like in the case of STL5, stereolithography. Yeah. The STL5 is the representation of a surface of a solid mortar. So just the surface, which contain a lot of triangular elements, yeah, combined together to form a surface, yeah, or multiple surface joined together. The higher number of the triangles, the better surface fitting. It means that the smoother the the motor, the smoother the motor. But then you have to how can I say, combat with the process of running simulation. Yes, because when you reduce the size of the elements, and then yes, you should guarantee that you have enough RAM, you have enough CPU in order to run the slicing process, running the simulation, and so on. And it's quite important to note here that the triangular, so the motor, the surface motor must be watertight. This means that there is no hole on the surface of the motor. And if the surface motor is not watertight, and then inside the package software which can prepare the motor before the 3D printing process, this kind of software can help you in order to fix the error regarding water type or non-water type. Do you get the point? Tôi nghĩ tiếng Việt sẽ giúp giải thích rõ hơn về vấn đề này. Ở đây là các cái software sử dụng computer để hỗ trợ cho cái quá trình design hầu hết, ví dụ như là Autodesk Inventor, SolidWorks, CATIA hay Z-Man, phần nhiều thì nó giúp chúng ta tạo ra những cái solid model. Tất nhiên chúng ta cũng có thể tạo ra các cái surface model phức tạp từ các cái software đó, nhưng mà tôi đang nói là những cái model tạo ra bởi những cái anh 3D modeling software như vậy thì thường là nó dưới dạng solid, và những anh solid mặc dù nó mỏng thôi nhưng mà nó vẫn là solid. Thì làm sao ạ? Thì nó không dùng trực tiếp để đưa vào cái hệ thống software của máy in được, máy in kim loại chẳng hạn, hay là các hệ thống additive manufacturing được, mà người ta phải convert, chuyển nó thành file STL, có nghĩa là biến từ solid model thành một cái surface model, có nghĩa là chỉ có các cái elements ở trên bề mặt thôi, và khi mà chia các elements này mà càng nhỏ thì đương nhiên cái surface của chúng ta nó sẽ càng smooth, đúng không ạ? Nó càng liên tục và nó càng smooth. Và mặc dù là nhiều các cái software có các cái khả năng khác nhau, đúng không ạ? Nhưng mà tất cả những cái software, tôi nhìn chung tất cả các software bây giờ ấy, thì đại đa phần đều có khả năng convert từ các cái phần mở rộng của cái software đấy sang thành file STL để có thể tương thích với các cái máy in kim loại hay máy in polymer có trên thị trường. Và sau khi mà chúng ta dùng các cái phần mềm design 3D, đúng không ạ, để chúng ta thiết kế ra chi tiết, thì đấy là một trong những cái approach để chúng ta có thể thiết kế. Tất nhiên là phương pháp gia công ngược cũng là một phương pháp này. Rồi chẳng hạn như các bạn dùng đất sét, đúng không ạ, chúng ta nặn ra những cái hình dáng rất là phức tạp mà thường là vẽ bằng tay nó cũng khó, vẽ bằng máy nó cũng khó chẳng hạn, nó gọi là freeform modeling ấy, chẳng hạn, thì trong những cái trường hợp đấy chúng ta hoàn toàn có thể nặn đất sét, chúng ta scan lại xong chúng ta in nó ra. Thì cái phương pháp gia công ngược đấy cũng không quá mới, cũng đưa ra trong cái thời gian gần đây, khoảng 5-6 năm hay là 10 năm trở lại thì đó, thì người ta cũng sử dụng. Có một cái vấn đề là gì ạ? Đó là khi mà chuyển cái ví dụ như tôi lấy ví dụ như các bạn dùng Inventor chẳng hạn, các bạn thiết kế ra một cái model 3D xong các bạn convert nó sang STL file, bởi vì cái STL file đấy thì nó compatible với cả additive manufacturing software. Những cái software mà dùng để control các máy in 3D ấy, là nó nhận file STL, thì thường là nó có thể không nhận file CAD đâu. Cái vấn đề ở đây là gì ạ? Khi mà các bạn đã convert nó sang thành STL rồi, nhưng mà cái problem nó ở đấy ạ, là mỗi một cái software nó sẽ dùng một cái thuật toán riêng để nó chia các cái phân tố ở trên bề mặt. Nó dẫn tới là khi mà import cái file STL này vào trong cái phần mềm mà dùng để control cái máy in ấy, thì nó sẽ phát sinh lỗi. Và những cái lỗi này thường là do lắp ghép những cái element có dạng tam giác kìa, nó bị hở, cho nên là cái model của chúng ta nó không watertight, có nghĩa là không chống nước. Nó hở thì nó sẽ sinh ra các cái lỗ, đúng không ạ? Và bắt buộc là các cái software đấy nó phải fix lại các cái issue liên quan đến cái việc không watertight để mà nó chạy những cái bước setup tiếp theo. Một trong những cái lỗi nữa mà software nó có thể detect được đó là cái vector pháp tuyến của cái mặt tam giác đó. Về mặt nguyên tắc thì các cái vector pháp tuyến này đều phải hướng ra bên ngoài. Vì một cái lý do nào đó nên cái vector pháp tuyến của một hoặc một vài các cái phân tố tam giác đó nó lại hướng ngược vào bên trong, thì software nó cũng giúp các em là nó chỉnh lại. Bởi vì làm sao ạ? Bởi vì những cái mặt tam giác, tức là có nghĩa là gì? Những cái mặt tam giác đấy có vector pháp tuyến hướng ra ngoài thì nó nhận đấy là mặt ngoài, của cái model. Và các em biết là gì? Những cái mặt ngoài của model đấy thì nó sẽ giới hạn lại cái phần không gian bên trong, và cái phần không gian bên trong thì nó chính là cái phần mà sẽ in vật liệu, sẽ điền vật liệu vào trong đó bởi công nghệ in 3D, đúng không ạ? Nên nếu vì một cái lý do đó, một vài cái phân tố đáng nhẽ là gì, nó hướng ra bên ngoài nhưng bây giờ nó lại hướng ngược cái vector pháp tuyến ở bên trong, thì lúc này một vài cái phân tố đó thì nó sẽ định nghĩa là cái mặt đã xoay ra bên ngoài ấy, nó mới là mặt trong. Thế thì hai cái phân tố ở cạnh nhau mà lại mặt trong mặt ngoài nó so le như vậy thì nó không nhận ra đâu là trong đâu là ngoài nữa, nó không in được luôn. Đấy chính là một trong những cái lý do mà cái bước repairing ban đầu đối với cả cái STL model nó cũng rất là quan trọng để đảm bảo rằng cái model của chúng ta có thể in được. Ngoài ra thì chúng ta có một cái model khác ở phía bên dưới, nó cũng là một cái STL file. Sau khi mà chúng ta thiết kế ra một cái 3D model thì chúng ta convert sang STL model, và chúng ta thấy là ở những cái mặt cong ấy, thì thường là để mà đảm bảo rằng là những cái mặt cong đấy nó rất là smooth thì chúng ta sẽ phải chia nhỏ cái phân tố của chúng ta ra, các cái element ra. Và như vậy là nếu mà cái số lượng element nó mà quá lớn thì các bạn cẩn thận khi mà xử lý đến nó sẽ bị treo máy đó. Tất nhiên là ví dụ nếu các bạn làm simulation hoặc dùng với Abacus hay với ANSYS thì các bạn biết đấy, đúng không nhỉ? Và ANSYS của chúng ta thì với student version nó cũng chỉ giới hạn khoảng 30.000 nodes, tương đương với đó thì nó chỉ khoảng đâu đó mười mấy ngàn elements thôi, hoặc có khi ít hơn. So now we'll continue with the representation of the STL file. It simplifies the surface representation. So for example, you could have the circle, two dots, a red circle, red circle on the right side of the CAD model. And when you convert to the STL file, and then you already simplified the CAD model because now it's no longer smooth, unless you introduce more elements to capture the curvature features of the circular outside, for example. And since you simplify the surface representation, some information, actually geometrical information, will be lost when storing in the STL format. Like, for example, the origin point. So a lot of points, yes, belong to the circle have been lost. The line, the datum, plane, material type, color, dimensioning, and so on. And we have limited resolution of the certain SDL model. As a result, unfortunately, it's a reason that the poor surface finish of the 3D printed part is formed. Yeah, unfortunately. The SDL model has problem regarding the scaling to high resolution of the lattice form. And this is the problem because when you convert into from the 3D model into the SDL model, generally speaking, you rough jam the surface. That's because you present you substitute the surface with a lot of elements, 2D elements, and if the 2D elements are large, and then you have quite rough surface. But if you reduce the size of the elements and you have quite large file in order to be run with the with your computer, let's say, or the software that you use to control the 3D printing process. And and if you have the 3D solid model, you convert into the SDL model, it's easy. It's easy, I would say. But once you have the SDL model and convert back to the solid model, yeah. If you can, you can try. You can try. You can see that it can significantly improve the file size. Improve your file size. So one time I have tried. I have the file of around 50 megabytes convert into the SDL file, and I select the file conversion in order to reduce the size of the elements, and then I try to convert back into the solid. And starting from the 50 megabyte file, after the conversion back to the 3D solid model, I have 1.5 gigabytes. And when I insert into the software that control the 3D printing, like for example, Autodesk Net5, and then uh, everything is suspended, yeah, blocked, because it's heavy file, it's a large file, cannot be handled by by the software. So I suppose it's quite large file. Quite large. So it's actually can be translated back to the original CAD file, but with the Rockgen surface, Rogenous surface. Because when you convert back the SDL model to the solid model, so the rough surface is kept, or the rough surfaces are kept. So these feature, the sub edge features, will be maintained. I would say will be maintained. Yes. So you can observe the solid model with similar shape to the original model, but cannot back to the 3D solid original model. No, that's impossible. And below you have two sequences that can be used to build part from the SDL model or solid model. Starting from the very first step to the S-build part. So for the first, let's say, strategy, we start from the scanning process, although that can be quite difficult in order to create by the software. So like using clay in order to create the part, we scan to have the point cloud, and using the software in order to translate the point cloud into the surface model, and afterward you convert to the SDL file and put the SDL file to the software, or use the SDL file as an input for the software, which can use to prepare the model for 3D printing. This step can create the support structures After considering, let's say, the orientation of the part with respect to the building plate, and to identify the down-facing surface, and to create the support structures prior to the 3D printing. And once you have the motor with support structures and they are okay, and then you can slide the motor. So it means cut the motor into different slices to define the cross sections, define the scanning area for the 3D printing process, and then you start the build. Yeah. And the other, let's say, process start with design concept, and this is actually the engineering process, normal engineering process, where we start with the design concept. We have the CAD, the computer aided design, or the computer aided engineering model. You have solid model. Yes. You have the CNC tooth part to cut. Yeah. And CAM model, computer aided manufacturing model, and then you have the part. Yeah. Just some information about the two sequence that can be used to build part from the SDL model or solid model. So SDL model is actually the surface model, and solid model is solid model. There's no, yeah. So I think, yeah, we can stop here and have a small break for 10 minutes, and then we can resume the lectures. Okay.